54. I'm very proud and happy to welcome all of you to the 54th session of our webinar series. We have started during the COVID pandemic issues when the whole world was tech, whole work was tech, and also our programs also were in difficult condition to conduct our space camps and other activities. Then we started thinking about a webinar series, and we started with support of Dr. Jayant Murthy from Indian Institute of Astrophysics. And today we have an important guest, Dr. Professor Satya Chakravarthy from IIT Madras. I am very happy to welcome him to our UL Space Club platform for the webinar series session 54 of UL Space Club. Welcome, sir. Welcome, Satya Chakravarthy, sir. We are very blessed with your guest, sir, to come here as our speaker. I met him. I met Satya Chakravarthy, sir, during the Huddle Global Program of Kerala Startup Mission. I was working as a volunteer at a program just near his talk. I could hear his interaction with other participants. So I was coordinating another event in the next hall. So I came to meet him and I requested him to have a connection with the World Space Club, and he agreed to take a session for our students, for our enthusiastic students, to nurture our ideas and to give us more technical ideas and guidance to explore the world of knowledge. So we are very happy with your guests, sir. Thank you for your blessing and your presence for our webinar session. And I welcome all other veterans from ISO who have been supporting our webinar series and all other activities. UL Space Club since the formation of UL Space Club, and welcome to Kudu sir and Shidil sir and all other members of UL Space Club. I welcome all coordinators and other participants for this session. So we are all set to start our webinar session. But before going to the webinar session, I would like to share you a few instructions for the new participants. First of all, we have a chat window here. This is an interesting topic regarding the 3D printing and modular launch vehicle technologies. So you will have plenty of questions to ask with our speaker. You can ask the relevant questions in the chat window. You can type it here, and our coordinators will select a few questions, and we can ask it in the question and answer session. If time avail you, we will avail you an opportunity to directly ask the question to our speaker. So that's it, and please don't try to switch on your mic and camera throughout the session. You can switch on it when you are asked to do so. When you are asking a question or when you have queries, you can ask with the permission. Otherwise, please try to switch off it because otherwise it will be an interruption to our participants when they are listening to our speaker. And please don't try to share your screen. Our speaker may have a presentation, so other participants will be listening to that. So if you try to share your screen, it will be an interruption to all participants and our streaming. Our webinar session is going live streaming in YouTube, so it will be an interruption to the participants who are listening from YouTube also. So please don't try to do that. These are the instructions for our participants. Please use this opportunity in the best way. Ask maximum relevant questions to our respected full speaker. So that's it. Once again, welcome to all for the UL Space Club webinar session 54. We have our mentor Shidil sir here to introduce our speaker in detail. I welcome Shidil sir to take over.
Okay, thank you, Varun, and good afternoon to all.
Sir, your mic is off.
Yes, thank you, Varun, and very good afternoon to all. And today we are sitting here in the 54th session of our webinar series. We started it when the COVID pandemic started here in 2020, but we could continue, and we are now to complete entering to the completion of the third year of sitting in these second Saturdays of every month. Regarding science, especially in the field of space, and our students are getting in contact with so many eminent people, scientists of India and our great institution of India. Today we have the topic with the mobile launch of 3D printed rocket engine based modular launch vehicles. It's a new innovative method in the field of space exploration and the technology here. And we have a great speaker from the great institution of India, that is IIT Madras. Professor Satya Chakravarthy is a professor of aerospace engineering in Indian Institute of Technology, Madras. And he's the first person from this great institution to our forum here. And we are happily welcome you to this forum on behalf of UL Space Club. And let me introduce this great scientist of India. He's received he's a bachelor from IIT itself in 1991, and his master's in aerospace engineering from the and doctor and PhD from the Georgia Institute of Technology, Atlanta. He's also working there, and now he is the lead co-founder and technical lead of E-Plane Company. It's a startup company aiming to make new breed of aircraft called hybrid aerial vehicles for vertical takeoff and landing as well as long distance flight to carry goods and passengers, ultimately leading to air taxi operation. It's a novel idea, a novel thing for students and for the space community. And he's the director of Agnikul Cosmos. It's another startup company aiming to make many long vehicles to launch micro and nano satellite into space orbits. And is the director of Aerostrovilos, a startup company aiming to produce fuel agnostic micro-gas turbines for decentralized power generation, including onboard hybrid electric trucks, and director of X2 Fuels and Energy, another startup company aiming to convert any kind of waste, municipal solid waste and agri waste into crude oil. It also is shareholder of advice to Galaxy EI, a startup that aims to make Earth observation satellites with multi-sensor fusion and edge computing in space. He is also a faculty member of Team Avishkar Hyperloop Student Team, IIT Madras, and now part of Tutor Hyperloop, a startup company to commercialize technology that is developed by his team. And interestingly, we could see that he's a scientist and he's also involved in a lot of innovative areas that culminated to the main aim of India, that's the startups and the industrial growth. That most of the students are making their heroes or role model from the Elon Musk, like that. We could feel we have such a person from India, and Elon, we can also proudly say he is also a replica of that great men of this world. And Satya Chakravarthy is interested in propulsion and combustion and researches on different aspects of combustion, gas turbine, rocket engine, and electric aircraft. He heads the National Center for Combustion Research and Development, NCCRD, at IIT Madras, the largest of its kind in this world. Recently, Satya Chakravarthy is also heading the Center of Propulsion Technology at IIT Madras, supported by DRDO. So we are proudly inviting again these great scientists to our forum, and I also invite all the dignitaries, all the scientists, veteran scientists of ISRO, working scientists of ISRO, teachers, students, and who are gathered here to hear the words of these great scientists of India, and this also make our students to dream a little bit more than what's the present scenario here. And we are thinking about the future and future of next decades of the space exploration in India. Then I once again welcome you, sir, to this forum for your great words. Welcome, sir.
Thank you so much. Can you all hear me, right?
Yes, sir. Yes.
Yes, we can.
Let me share my screen. Are you able to see my screen? Right. So thank you so much for having me in this series of talks that you have been arranging. Let me congratulate you for, first of all, doing this. It's a great service to a lot of school students. I'm particularly congratulating the veterans who are mentors in the school that is supporting this and so on. So thank you so much again. The topic that I had already informed the organizers was mobile launching 3D printed rocket engine based modular launch vehicles. I'm S.R. Chakravarthy from the National Center for Combustion R&D at IIT Madras. Let's start with the bigger picture on what the space tech entire set of segments of technologies is all about. The starting point is for us to be able to set up a launch pad and offer launch services, make a launch vehicle. The launch vehicle will carry payloads. These payloads are typically what's called as satellites. It could be other payloads as well, including humans. But in this slide, we just focus on satellites. The satellites have a data uplink and downlink with the ground segment. And they then, the downlinking essentially comes down to putting out output in terms of remote sensing, communication, in-orbit missions, and new age space applications. These are typically the payloads that are there in the satellites. And the ground application, ground segment, once you get the data, there is the data processing that happens, and there is analytics of the data that happens, and you provide insights. And this is done by external developers who use this data. And the analytics is used for lots of different applications like debris monitoring, construction, agriculture, mining, and so on. So the entire value chain actually starts with launch pad and launch vehicles. That is what we call as the upstream segment. The satellites and the ground segment and all the payloads is typically called the mid segment. And the data processing and the analytics, insights, and the different applications in which they serve is called the downstream segment. So what we are going to focus on is primarily something to do with the upstream segment. Before we actually get into that, we have to actually look at what are the different characteristics of spacecraft that are there. And on the x-axis, we have in this graph the space, what we call as the bus mass, which is essentially the total weight of the satellite. That's what we call a spacecraft bus mass. And then the question is, what is the cost of these? The cost is actually represented by millions of dollars. And you can see a band of the graph that is going there. It's a sort of a qualitative band, but the x-axis and y-axis are fairly quantitative. You get an idea of what is the kind of size and cost, the weight and cost that we are looking at. Based on this, we can classify these as what's called as microsatellites under 100 kgs of satellite mass, small satellites up to about 1,000 kgs, and large satellites beyond about 1,000 kgs. You can also classify them based on where they are going to in space. LEO is low Earth orbit, medium Earth orbit, and then geostationary Earth orbit. So these are progressively farther and farther out in space. And most of these are actually targeting the low Earth orbit. And there is a small segment of large satellites that go into the medium Earth orbit. There are some small satellites as well as large satellites that target the geostationary orbit. And then you have a lot of subsystems that you can think about: space control systems, small civil science missions, Department of Defense technical demonstrations, large civil science projects, and commercial geosystems. Now, in this slide, we again characterize the different divisions in terms of the payload mass, which is the satellite mass. So we now distinguish this in terms of three parts. One is less than 250 kgs. The second one is 250 to 1,000 kgs, and the other one is greater than 1,000 kgs. So the middle one is actually more like a small satellite variety. The right one is the large satellite variety. The left-hand side is slightly more than the microsatellite. Microsatellites, there is no hard and fast rule that 100 kg is where the mark is, but we just accommodate up to about 250 in this particular chart. Now, what we have actually positioned here is several logos for launch vehicles. So these are actually rockets or rocket company logos, if you will. So we have things like Agnicol, Astra, Orbex, Rocket Lab, and so on for the small launcher variety. The reason why we are actually saying we want to keep up to 250 kgs is there aren't too many rockets that are taking exactly up to 100 kgs. So Rocket Lab carries up to about 150 kgs, Astra carries up to 250 kgs, and so on. So that's the reason why we have actually put at least a few numbers in the left-hand side. But now if you look at the range of 250 to 1000 kgs, there are a significant number of rockets that are available for carrying these kinds of payloads. You can see Skyrora, PLD Space, Gilmore Space, Firefly, Skyroot, and ISRO. ISRO is now making a rocket called SSLV, Small Satellite Launch Vehicle, which caters to satellite payload weight category in this range. Up to somewhere between about 300 to 700 kgs is what they would do. Now, the traditional PSLV that ISRO used to do can also do this by removing the strap-ons and have like a core alone booster and all, but it can still do much more than, it'll be more closer to the 1000 kg rather than the 250 kg. So for that purpose, ISRO has actually configured something called SSLV. I'm not very sure if many of you know that there are so many companies that exist around the world, and in India as well, Agnikul and Skyroot, for example, that are in the job of trying to launch vehicles, satellites. The right-hand side is a little bit more well known because that has been the case in the last several decades, where the large satellite is actually the main play that's been there. ISRO has been in that game. SpaceX has been a newcomer in this game, but doing it very effectively. Ariane has actually been doing a good job. There are a few others we can put, put Long March from China, or the H2 vehicle from Japan, and all those kinds of people as well. Relativity space is actually something new that's coming up in this orbital class, and so on. So there are about 25 plus launch companies that have been registered globally, but have not made any significant progress in the last 2 years. Now, the same map, right? So the x-axis remains the same, which is less than 250 kgs on the left side. In between is 250 to 1000 kgs, and greater than 1000 kgs is on the far right. But we now have a y-axis. Previous slide, we did not have any y-axis. We just had scattered and sprinkled many of these logos to slot them into left, middle, and right. But we now try to put a y-axis here, and that y-axis is sort of like what's called as a waiting time to launch. What is the wait time that's required if I have to use your launch vehicle is what is the question that we have to ask any one of these people. So the lower it is, then the wait time is very less, is the point. So now what you have to understand is Agnikul actually shows like a very, very low wait time. Astra is next. Orbex is somewhere in the middle. We're not putting numbers on this waiting time, but we will actually talk about some numbers in the next upcoming slides. What we're talking about is somewhere between 2 weeks here to about 78 weeks there. 78 weeks is almost, it's about 1.5 years plus, right? That is the kind of waiting time that we would be looking at between Agnikul and let's say the ones that will require you to wait very long. From the time your payload is ready to when you will actually end up launching. So you will find that most of these larger and larger rockets actually have to go through, get you to endure larger waiting times if you're bringing your satellites. And that's okay because they make only a few satellites of the large category. Whereas on the small side, you have large number of small satellites. So to make all of them wait for longer periods actually makes little sense. So that is the point that we would be talking about in a few more slides later. But before that, let's also actually look at where we would like to launch this from. And this is a very interesting chart here. So this shows the world map and points out that there are about 77 launch ports available for orbital and suborbital launches. In India itself, you can actually see about 3 points that have been mentioned that are black, that are sort of like saying they are current launch pads, right? So the current launch pads here are essentially Tumba's equatorial launching rocket station, the Turles rocket launching station. There is Turles in next to VSSC or part of VSSC now. where they have been doing a lot of sounding rockets. The other one that is slightly to the northeast of that is Sriharikota, which is India's primary spaceport. The third point that has been mentioned there is actually where most of the missile testing happens by DRDO off the coast of Orissa. And there is also one more in orange that has been positioned here, which is an up and coming or a proposed site as it marked here in a place called Kulasekarapatnam next to Thoothukudi in Tamil Nadu. But aside of that, there are several other places that have actually been marked as either existing or proposed, up to about 77. That's what is the overall current scenario. So based on this, we want to actually go back to what are the bottlenecks that actually are posed for launching satellites. So this is a pie chart that gives you lots of different excuses and reasons, if you will, on why launches get delayed. So in this, we have actually circled about two of them, two major chunks of reasons. About 6% delay days and 8% because of earlier launch vehicle anomaly, and then launch vehicle manufacturing and launch vehicle development. You can also see the number of satellites, small satellites that have actually got affected by these delays. Right, about 121 small sats, 421 small sats, 80 small sats. So that constitute about these different percentages. That on a total of about 34% of the launch problems is because of lack of launch vehicle on demand. When you want, it is not available. They are still making the launch vehicle and so on. On the other side, there are, of course, a few other things like 13%, 1%, and all those things. But the other major thing is actually 40% of the launch problems are actually due to what is called as ride sharing. And we will talk a little bit about this ride sharing in the next few slides to understand what that exactly means. So basically, both 34% and the 40% put together is close to about 75% of all the launches are actually delayed today due to the way the launch services, the launch vehicle, all of these things are constructed. And this comes from the construct that was there when the typical launches were few and far between, with very large satellites and few of them to be launched. So to just give you an example, today, for example, a satellite could be like as small as something that can fit on the palm of a person. And here we are actually looking at a very typical small satellite, and you now have this unit called U. A U essentially is a particular cube called for a CubeSat, and it weighs certain amount of mass. And a 12U CubeSat with a dispenser is essentially the one that ejects it into the orbit, is something that will be of the order of about a 0.4 meter by 0.2 meter that would actually sit in the typical payload fairings of current large launch vehicles like Ariane 5 or a Falcon 9 or a GSLV or a PSLV as shown here, which is very, very small when compared to the entire payload fairing, right? So this is sort of like saying that if I were one passenger and there is like one train that is going there, and I want to actually take this train ride right now, I want the entire train to actually go with me for just for me. So obviously that is not possible. Trains will run only when they run. I have to actually find a seat. I will have to hope that a lot of other people are also wanting to come along with me, and therefore the train run will be profitable for everybody, and all of those kinds of things, which means that I can go only when the train wants me to go and not whenever I want. It's not a taxi, right? So a taxi is where I call the taxi or auto rickshaw and can actually go whenever I want. This is what it is. So let's just look at what is meant by a ride share in that case, right? So this is actually, I think right now we have PSLV has launched more than 50 times. So this is, I think, one example from the C-34 launch. Just show the picture. This particular mission was carrying what's called the Cartosat 2 series satellite that you can see is sitting hugely on top over there near the payload fairing. And right below that, there are a whole bunch of other satellites that like the Satyabama sat, the Swayam, Lapan A3, M3, MSAT, and Dow QP2, Dow QP1, 4 numbers of each at the bottom, just above the instrumentation bay of at the bottom of the payload fairing. Now, a typical CubeSat, as I said, can be fitted into one's palm. That's the kind of satellite miniaturization that's happening today. And it could take anywhere as short as like about 6 months to build, but you will wait for another 1.5 years, as I said, the 78 weeks that I mentioned, to launch, right? And once you have to, the reason is they are actually accumulating a lot of small satellites along with one major customer, and then trying to get a forced ride share. All of you should actually go together. Now, the problem with that is all of these small satellites should also make sure that they don't have any electromagnetic interference problems with the main satellite, and so on. So that the cost of developing these satellites also, and then maintaining them for the remaining 1.5 years, becomes extremely huge when compared to the cost of building and launching that alone. Now, so if you now look at, okay, so is it like a really big problem, or is it a big opportunity here? So the small satellite market is actually something like about a $2 billion market in the world. And by about 2025, we expect this to actually become like a $4 billion per year kind of thing. And you can see how the projections are in the last 3-4 years, 2 to 3 years, and going all the way to 2025. You can see there is an uptick on the number of satellites that are projected. And many times when we are like, for example, at the end of 2022, we go back and check whether these numbers have actually fructified in reality because they are past. And what is in the future is still a projection, and so on. And we find that many times these projections are actually very conservative and underestimates the actual launches are more than what was projected. So we expect that that trend may continue further, and therefore you can see these peaks to be even sharper going forward. Most of these sectors are primarily, like as you can see, the blues and the red are primarily communication and Earth observation. Then there are a few other things. IoT is now emerging, as you can see, projected, the orange one going forward. So so what do we do about this? We want to essentially make a rocket that will be about 40 times faster to launch. Instead of having you wait over 78 weeks, you would like you to wait not more than about 2 weeks if you're coming with a satellite. And the second aspect is that the rocket actually itself is scalable between about 3 to 300 kgs of weight at the same price point on a per kg basis of the payload. And I'll explain that in a minute. And therefore, it makes it about 10 times cheaper per vehicle and potential for high margins or lowest cost in the world. So we expect that we can launch the cheapest in the world in the small satellite segment to begin with at the moment, right? So what is this rocket made of is essentially 2 stages. One, the first stage consists of about anywhere between 4, 5, 6, or 7 engines, each of which actually produces about 25 kilonewtons at sea level. It's an electric pump-fed cycle engine. That means we don't have additional combustion that is turning a turbine and all that stuff. It's an electric pump that's powered by a battery, and that will turn a pump, and the pump will actually pressurize the fuel and the oxidizer and pump them into the combustion chamber of the rocket and so on. These rockets are also what we call a single-piece semi-cryo engines, and these are 3D printed completely in that one single piece. So we will talk about that also in the next few slides. The second stage in this rocket is called Agnilet, which has a 9 kilonewton. It's a single engine stage, which has and that engine has a 9 kilonewton thrust at vacuum and electric pump fed cycle, single piece 3D printed semi-cryo engine. So this is how the rocket looks like. So the left-hand side actually shows you only the second stage and the payload fairing together. The right-hand side picture actually shows exactly the same thing to the left, and then there is, of course, a gap to show what is in between. Of course, it will be covered in reality. The rest of it on the right-hand side, or it's been a bit staggered. It's been kept a little bit staggered. The nozzle will actually get inside this first stage's stop. So this point will actually come and meet with this at the flange there. And the total length of the rocket, this is actually a 1:1 picture. We will show you another picture of this where some human beings will be standing in front, particularly the Prime Minister of India. So you can get a sense of the size of this. But this is typically about 18 meters tall. That's probably about 4 to 5 story building, maybe about 3 to 4 story building kind of height. And it's about 15 tons in weight, total weight, for carrying up to about 100 kgs to low Earth orbit. This is the rough configuration that we're talking about. So in this case, then, what happens is it's still a very small rocket when compared to the full rocket. So if I were to actually compare with the previous picture of a CubeSat that is positioned in these different large rockets that are currently available, this CubeSat will snugly fit into exactly this Agnibahn's payload fairing. As you can see, drawn to scale with respect to the other payload fairings, but on a blown up view, you can see how it actually occupies pretty much the whole of the payload fairing there, right? Now, we want to ask the question, why are we actually doing something called semi-cryo, and why are we actually doing a 3D printed rocket? That's another question that we want to ask. So for that, we make a very simple comparison between solids and liquids. And we now look at about 3 or 4 points. Typically, some of these points are actually not considered technically. They are more commercial points, but very important to consider when you want to go and operate these rockets. The first one is actually more of a technical point, but has a implication on the performance. So the complexity and the number of parts, liquids actually have a problem. But I also would like to take my rocket elsewhere and launch it from one of those 77 launch ports around the world. A solid rocket today, I don't think can be exported. So we have a restriction over there. So that's a red mark for solids. That's something that a lot of people don't bother about or think about. Similarly, mobility and insurance and running costs, because solids already have the propellant inside, right? They are a explosive class, and therefore there is like a lot of safety requirements. Therefore, the running costs, the handling costs, and the insurance for the movement of it will actually be a red. And flexibility and scaling down, and we will talk about this significantly in the next upcoming slides. Once you have made a solid rocket, that's it. That's what it is, right? So you can't change anything there. That's again a red. So what we would like to do is to look at this first red for liquids and then see if that can also become a white or a gray, right? That is, remove the red there. And that's the reason why we want to actually make a 3D printed rocket. So we are de-risking the complexity with 3D printing by having a single piece 3D printed rocket that you can see on the left-hand side that is kept upside down. That is the exhaust, the nozzle is facing upward. And this actually integrates about 1,000 parts to one, right? And what are these different 1,000 parts? Is like an igniter, about 100 plus cooling channels, 70 plus plumbing passages, 8 injector elements, each of which has about some 3 or 4 parts by itself that are high precision and highly precision assembled, and so on. These are 8 actually for the top stage. For the lower stage, it's actually more like about 48. And so that means that much more, like about 48 times 4 number of parts there. And the combustion chamber, the nozzle, and all of these things are actually printed in one shot as a 3D print in a 3D printer. So we have that facility with us where we can actually develop these 3D printed rockets. So you can see that we have printed like so many of these different rockets of different sizes and capacities and so on. And we have done lots of firings of these rockets at our IIT Madras facility for repeatability, thermal qualification, reliability, and so on. So how do I actually get this particular thing about launch when you want? Is I can print a rocket whenever you bring the satellite, I can then start printing the rocket. Each of these rocket engines takes about three days to make, and I have to make a total of about and I can make about 2 rockets simultaneously, 2 rocket engines simultaneously. I have to make about 4 of them. So I have to do I have to make these rockets over about a 12-day period, assemble them, and I'm good to launch. This is what the picture is. So I can also configure the rocket and launch what you want instead of not only when you want. So we will do launch. We can do launch when you want. We can do launch what you want. We can do launch where you want. So these are the 3 things that we will be talking about. So what you want is if your satellite is like about 30 kgs, right? This is about the cost. If the satellite is about let's say 100 kgs is the cost. You can see that the market value right today is actually going like this. That the reason for that is you have a smaller satellite or a larger satellite, it doesn't matter, right? You essentially end up using the same rocket to launch. So on a per kg basis, the launch cost actually goes up for a smaller satellite when compared to a larger satellite. That is the reason why there's like a hyperbolic kind of a curve that is there. Now, what we do is we bring down this cost by tailoring the rocket or customizing the rocket to suit the payload. And how do we do that is we keep a bare minimum of about 4 rockets as a minimum, so that they are used for gimbaling and controls. But if you want to actually have a little bit more payload, we can take a 5th one. You can put a 5th one. If you want a little bit more payload, you can remove the center one. You can put 2 more on the sides to have 6 rockets. And this is in the first stage, right? And if you want to take a little bit more, you take all 7 rockets and so on. So this is how we actually achieve like a very flat cost curve by modularizing the rocket with 3D printed engines. And similarly, I also talked about a launch where you want, which means that the entire rocket is actually placed on a mobile launch pedestal, and you can drive this to wherever you want. And of course, it can be containerized. You can put this entire container on a ship, and then it can be shipped to some other country where that can be launched, and so on. There is no fuel or oxidizer to be taken along with this. So it will be basically like a piece of metal, like a car engine, let us say. Therefore, there is absolutely no hazard in transporting these things. So on the whole, what we are talking about on the novelty of these rockets is a complete rocket engine in a single piece, 72 hours to build, no human intervention, error-free fabrication, 2 weeks to launch, cheaper insurance, hard to replicate. Plug-and-play vehicle configuration, cheaper to build, redundant architecture, customer-centric vehicle, flat cost curve per kg, hard to replicate again. And mobile, rapidly erectable launch pad. So we have, I'll talk about it in the last slide, we now have India's first private launch pad that is set up in Sriharikota exclusively for launching these Agniban rockets, which is very, very small. It's about some 800 square feet or something. It's approximately the size of like a 2-bedroom apartment. So that's very small infrastructure that's required. We essentially can start off with a barren piece of land and move into it with containerized rockets and start launching, right? So this shows, in fact, we don't have I think the last slide is where we will have the picture of the launch pad that has to be integrated into this. So the combustion center, the NCCRD, is where we used to be doing the design and development. We now have test facilities over here. Each of these test facilities basically has containers, and these containers is where people sit inside and then do the work as well. And even the mission control is basically a container. We have an assembly facility that's coming up in North Chennai on the way to Sriharikota, so that the assembled vehicle can actually be taken by truck to Sriharikota. At the IIT Madras Research Park, we have something called the Rocket Factory 1, that where we make the 3D printed rockets. I'm going to skip a lot of these upcoming slides because they are just way too technical at a school level. But I'll be happy to answer any questions that somebody has. So just to show you what we have, this is basically the configurations that we have on the first stage and the second stage, and a lot of numbers associated with that. What is the stage 1 engine configuration? What is the stage 2 engine configuration? Then how is the structural subsystems look like? More of that in this. The aerodynamics of this entire thing. avionics overview, the block diagrams for what goes into the avionics packages, embedded software, what is actually there in this, and the power architecture, how are we distributing the power that's there, what's the power budget that's available for different aspects of it, and then the navigation systems and so on. And finally, the telemetry tracking and control communication, right? So that is the subsystem there. So I think these are the last couple of slides. We can stop here for now, and I'll be very happy to take more questions instead of having to give a longer lecture. So this essentially shows the kind of what should I say, encouragement and recognition that we have been getting so far. This is the picture right hand side. I said that the Prime Minister has posed along with this entire rocket. So you can see that how big it is when compared to a typical human size. And very similarly, we've also been working with ISRO to get one of the static testings done at VSSE. We also have the flight termination system provided by ISRO to integrate with our rocket, so that if it has to go wrong, veer away from its intended trajectory to any hazardous sites, then we will terminate the flight by and then blow up the entire rocket into pieces. On the bottom right, we can see the picture of India's first privately developed launch pad at Sriharikota. I think with that, I think I'll thank you for listening, and we'll be very happy to take some questions for some time. Yeah. Yeah.
Thank you, Shajil Marsh. See, this day, this afternoon has been something quite unique for us. In fact, we have been having rocketry launch vehicles, satellites, and its technologies and launchings, a major part of our talks. But then the approach today we had from Professor Chakravarthy has been something very, very unique, very, very different from what we have gone through so far. More than I'm commenting on that, we have got Vijay Bhatt, Sundaramurthy, etc. here. I think they will be able to give a very good outlook on how the whole thing has been seen by the professor, and the students should ask the questions. Actually, we should not come in the way of their asking doubts and questions. But something very unique in today's thing is the technology, the complex technology being visualized as a means of doing things with extremely little complexity and extremely reduced cost. 3D printing is a media which is being discussed today here. In fact, not much has been thrown open to students on this area. So I think it's a beginning, and I thank very, very much to Dr. Chakravarthy for presenting this topic, particularly coming and presenting to us, our students, itself is a blessing for us, and more so of a topic of this nature, which is going to be the hereafter for the technology to flourish, and multiple launches, and probably every day itself multiple launches, and space is going to be a thing to be watched. How multiplier it is going to be in terms of the technologies and the facilities which we are going to get. So thank you very much, Chakravarthy. Has been a very, very nice thing, and we are indeed grateful. And I am also thankful to Varun for knocking at the door of Dr. Chakravarthy at the right time. He got an occasion to get across him and try to cash in for the benefit of the students. It is so nice of Varun also, of his thoughtful action, timely action and all that. So I request Vijay Bhatt to comment. Vijay Bhatt. What's up? Oh, yeah, he is Samadhan. Correct. Hello, TK Sundaramurthy. Please come.
Good afternoon, sir. It's really a great day because so far, okay, what we were seeing were all in parts of our space technology, especially, okay, I'm familiar more with satellite systems and then the building of satellites and other things. And of course, yes, I have chances of getting into launch vehicle reviews and other things. But today, Chakravarthy sir has really given a very good picture about the launch vehicle developments and how it is being done in a cost-effective way using 3D printings. But okay, he has given a nice idea about the entire launch vehicle fabrication process. So it's a very good information for all of us. It's really quite interesting, and in fact, I'm more interested in knowing more about it, and I think probably I will try to contact him personally after this meeting, because I request Satish Sap or Kuti sir to share his mobile number so that, okay, I can, because you know my interest, so that is the thing. I have a couple of questions to ask, sir, if you please excuse me if I'm immature or, okay, may not be knowing things. Okay, so one thing which I would like to now see, now the engines have been fabricated and it has been tested. Now, stage levels, how many tests have been done and how long now you are estimating it will take to assemble a test rocket, and then you are planning to have a launch?
Right, sir. So this is the first question, right? So the quick answer is the second stage is getting ready because that's easier to do. Always do the easy thing first. And so we have got that launch pad, as I said. So I think sometime in the next 1 month, approximately 30, that is the next 30 days or so, we expect to actually go through what's called the suborbital launch with the second stage alone, because the second stage will not take us to the orbit. So we will be trying to do the suborbital launch with the second stage. The first stage rocket engine design is all complete. We have to start doing the 3D printing. We have been doing the pump development and testing. The pumps are also 3D printed. The motor casings are 3D printed. So lots of those things are all 3D printed. So we are doing a lot of pump testing so that we can get the first stage single rocket also ready first. We have a test stand that is being ready for testing that. And we've also actually got space developed for the 7 cluster entire first stage engine to be tested. So all that infrastructure is being developed in our campus for this purpose. So we expect that, I think, if we are able to do the first stage in single engine in the next few months after the launch, the suborbital launch, then we do the cluster testing. We should be ready with the first stage also. So before the end of this year, we can try to do the full orbital launch vehicle, 2-stage launch to orbit.
Oh, thank you so much for your update, sir. We are all very eager to see. Of course, suborbital flight already we have seen one. And now, anyway, you have established the launch pad in Sriharikota. Of course, yes, we are all again very eager and also be happy to see such a kind of a progress. In fact, such a kind of rocket building by private people, especially the academic community, that is really, it's quite encouraging, and it is very interesting to see. Anyway, we'll all pray God. I think you would be successful and try to have, we are all very eager to see the first launch. Okay.
Thank you, sir.
Thank you very much for your kind answers, sir.
Thank you. Shall I just read? I think there are about two or three questions there. I think the first question that we have is.
Yes, sir. Yes, sir. I would like to invite our student members to handle the question answer session.
I think Dr. Chakravarthy himself wanted to
So
handle it.
our first question in the chat window, we have few questions here.
Yeah.
The first question that we have is here is what are the basic materials used for rocket making? The basic materials used for it.
Right. So it depends on whether it is a solid rocket or liquid rocket. A solid rocket. So most of the rocket actually is rocket engines, the propulsion. And then you have the payload, and you have the controls, the avionics, and so on. So if you now look at the rocket, propulsion being like the biggest part of it, depends on whether it is a solid rocket or liquid rocket. Solid rocket, most of it is actually the propellant. The propellant is usually what's called the composite propellant, that is made of ammonium perchlorate, hydroxy terminated polybutadiene, that's a polymer, and typically aluminum particles. So that is the main thing. Whereas if it is liquid rockets, then the materials used are typically for the rocket engine itself. You use metal. In the case of what we are doing, we are essentially 3D printing the rocket with a high-strength stainless steel alloy called Inconel. That is the material that is used. In addition to that, we use stainless steel or aluminum, depending upon the temperatures involved. We use them for pumps, and then we use the composite overwrap pressure vessels for storing the fuel and oxidizer. So these are the typical materials that we use.
Thank you, sir.
Thank you, sir. And so there is another question raised from one Mr. Agner. The question is 3D printing rockets engines are reusable?
Yes, they are. We have in fact been doing several tests with the same 3D printed engine again and again for multiple different durations and so on. And before we launch, we can actually test the same hardware on the ground before we get it to launch. And if we are able to recover that engine after the launch, we can go back and use it again. Yes, the answer is yes.
Yes, sir. So these were the questions in the chat windows. So I would like to invite other students. You can ask the questions directly to the speaker right now. You can raise your hand, or you can switch on your mic directly, and you can ask the questions. Today we have an excellent speaker here, respected personality. So use the opportunity in the best way. Ask your relevant questions, clear your doubts.
I think there are a couple of more questions that are there in the chat window. Trisha and Prachi have asked some questions. Right?
Yes, sir. Right now, Trisha and Prachi can switch on the mic, and they can ask the question directly. Trisha, you can switch on your mic and can ask question directly.
Hello, sir.
Yeah.
My question is, how the communication and navigation on the payloads work?
The communication and navigation on the payload. Don't quite understand the question. So typically, communication, there are communication. I mean, are you talking about the, no, wait a minute. Let me try to understand the question. So the payload is essentially, the payload for the rocket is the satellite. Okay. The satellite could be a communication satellite by itself, or it could be imaging, Earth imaging satellite, or lots of other applications are there. But all these satellites will have to communicate their data back to the ground station, and also take commands from the ground station communicated back to the satellite. So that is the communication part over there. Then, so this is actually done directly. So there will be huge antennae that are there on the Earth at different points. You'll have what's called as Earth stations that are trying to cover a direct, what we call as a line of sight way of communicating with microwave signals for communication. That is what is done between the satellite and the ground station. And the other thing is the navigation. So navigation has a bunch of different components, but typically what we use is what's called as inertial navigation systems. So the satellite essentially has accelerometers that are there inside the satellite, which will govern what is the different, as the satellite moves, it actually senses what is the acceleration. Then you do a double integration to find out like what is the position. And every time it moves by delta t, you actually find out like what is the next position, the next position. And this has to be corrected by a backup option on positioning the satellite. So that is typically what is done for navigation.
Okay, thank you, sir.
Raji, you can ask the question now.
Good afternoon, sir.
Mm-hmm.
Sir, I have a doubt related to like 3D printing satellite. Why they are given the name 3D printing? Is it related to printing or something else?
It's related to printing.
Printing in the sense, sir? Like, will it print some pages or will it give 3D image to us?
Okay, so what you do is, so if you come to IIT Madras and see this 3D printer that we have, so you have, just like how your 3D, your paper printer, you have the paper in which things are printed, we have a platform in which a thin layer of metal powder is spread by a spray. Right? So you'll have one sort of like a rod that sprays the powder all along across this bed. So you have a very thin layer of powder that is uniformly spread over there. Then a bunch of lasers actually come or are shining on this, and these lasers actually take these powder particles and melt them and sinter them together and weld these metal particles together on that particular surface. Once that weld, and this is done only where you need to create this 3D printed material. Once that is done, then the entire bed moves down, and that is whatever has been made, right, as that moves down, or rather the bed moves up, the material stays there, or whatever it is, and you now have a fresh coat of powder that is sprayed again, and the laser comes and then welds the metal powder that is there on it wherever we need to actually produce this object, and those are in turn welded back to the previous layer. So likewise, you are actually building this material layer by layer by spreading powder and melt and laser welding the powder particles wherever required to form this entire structure. So instead of actually getting a 2D print, you actually get a 3D buildup of this material, but it's actually done layer by layer as if how you are doing printing on a paper.
Okay, sir. Thank you, sir.
Thank you.
So, thank you, sir. And Adidev, you can ask your question now.
Hello, sir. Am I audible?
Mm-hmm.
Sir, my question is, will these 3D printed payloads last like other non-3D printed payloads?
Yeah, that's how that is the starting point for us for our testing. So we make 3D printed samples and test them to make sure that they will behave exactly like the non-3D printed ones. Yeah.
Okay, sir. Thank you, sir.
Sir, I have one alternate answer for 3D printing to tell the students it's like what is happening. And you take as an example one tumbler. Okay, if I want to make the tumbler in the 3D printing mode, what has been done is the base of the tumbler is been first made with that powder coating, and slowly the tumbler is been that height has been slowly grown again by throwing the dust, and then the laser particles will connect, and then this is how that tumbler is growing from the bottom till the top. So by this method, what we can do is, in earlier modes, whatever the material which are used can be minimized, and whatever required only will be used. So that is the very big advantage of having a 3D printer. Next one is, it will give you a precise dimensions and the shape. These are the very important thing for our rocket or satellite, whatever it is. I think this will be giving some idea what is the 3D printing. With the 3D printing, how things are being made. Thank you. Sorry for the intervention.
No problem. It was actually a good example. Very good. Thanks so much.
Thank you, sir. So is there any other question? You can ask it directly. You can come forward and switch on your mic and ask it.
Excuse me, sir.
Yeah.
I'm audible?
Yeah.
Yeah, sir. What's the disadvantage of this 3D? Disadvantage
Of 3D printing?
Yeah.
Yeah, so it's actually still a slow process. So if I have to, for example, I have to take the example of a tumbler, right? The current way of making the tumbler is it's what is called as metal forming or sheet metal work. You take a sheet of metal and then you position it on a die, and then you have a punch that will actually come and punch it, and you now get the metal to form like that. So with this, I can actually make literally hundreds of thousands of tumblers per day if I have to do that, right? And this is typically how production happens. There are no moving parts here. There are no assembly here. There is not much precision required, right? So no problem.
Yeah.
Whereas if I have to do a 3D printing of the same tumbler, it may take us almost like a day. One tumbler could actually take like a day. So currently that is a major problem. So, and then it's also expensive to make it this way. So when do we actually have to resort to 3D printing? Is usually today, in today's world, when you now try to develop prototypes of your designs, where your design may not be frozen, so you cannot actually have a die and a punch for that particular design. And you don't know how the next prototype is going to be because you will change the design. Then you have to make another die and another punch for it. So instead of that, you will want to actually quickly do a 3D printing of that particular geometry, test it, and see if I have to change the geometry and so on. So during the development process of a technology or engineering, 3D printing is quite useful today. But it will not be very useful for mass production, unless like what we're doing in rockets or jet engines and so on, where the components are very, very expensive. The entire product is very expensive. Rockets or jet engines are very expensive. And given the amount of money involved, I don't want to be spending on uncertainties in precision manufacturing and precision assembly. So if I have a large number of very precision, high precision parts that I have to make, and then I also have to assemble them very precisely, there are room for a lot of errors. And those errors will actually multiply if the parts are made erroneously and assembly is also done erroneously. And in fact, that takes more time. So to check, verify, and then assemble, and then verify the assembly and all those things. So there is like room for errors. So in that situation, we say it's better to actually give it like one full of 3 days in which one entire rocket engine can be made, because in conventional way, those many small parts we made very precisely and assembled to make an entire rocket engine will take much more than 3 days. So that is the combination of factors that makes you decide whether you want to do 3D printing or you don't want to do 3D printing.
Thank you so much for clearing my doubt, sir.
Thank you.
Thank you, sir. Is there any other questions, or can we move on to the next session?
Hello, sir. Can I audible?
Yes.
Sir, what are the advantages of GSLV and PSLV rockets?
GSLV and PSLV rockets are meant for fairly large satellites. I think PSLV today can take satellites. Depends on the orbit, right? So typically PSLV takes satellites to orbits that are around, let's say, 700, 800 kilometers above Earth's surface. And the satellite mass that can take, I think today is actually continuously increasing. It's more than about 1,500, 1,800 kgs. So they are in the large satellite category. GSLV has now graduated from a Mark II to a Mark III. Mark II used to be about some 2,500 now kgs. Mark III can do about 4,000 kgs. The word G actually stands for geosynchronous launch vehicle. So that is meant for positioning satellites in just above the Earth's surface, so that as the Earth turns, the satellite also will turn around exactly, so that it's always looking at only one place. This was the original concept, but these rockets are quite versatile. A PSLV can launch a geosynchronous satellite, except that the mass of that satellite will be very low. A GSLV can actually launch a low Earth orbit satellite, and that will be actually extremely high, very high launch mass with the satellite mass there. So both of them can do eventually large satellites, let us say.
Thank you, sir.
Thank you.
Hello, sir. Good afternoon. Good evening.
Mm-hmm.
Myself, Ashwati. Sir, how does the design of the engines work on? Is any similar? Is all similar to the normal vehicles, or any special for the 3D printed rocket engine?
More or less the same. You still have the same concept of combustion chamber, nozzle, injector plate, all of those things exactly the same. There are some special efforts that you have to take for 3D printing. For example, the tumbler example that we have, the tumbler is actually somewhat shaped like that, right? So as you are now printing more and more, there's a chance that this powder will actually fall off. So anything that is actually going to be more like shaped like this, you may not be able to actually print more like that. It'll be better if you actually keep printing like this as the layers add up. So the top layer should actually sit on the bottom layer. So you can't have a layer that is outside of the top. So what they do is they actually give some kind of supports. And these supports may not be part of the original design. So they are extra pieces. So after you have made the entire thing and it is solidified, you can cut off these supports and remove so that you can save the weight. But that is a wastage of material. Whereas originally 3D printing is supposed to use exactly only that much amount of material that's required and not waste any more material. So there are the support structures that you will have to design additionally with some complicated geometries.
Okay, sir. Thank you.
Thank you.
Thank you, sir. Is there any other questions you want to ask?
Sir, can I ask a question? Am I audible?
Yes, Abraham. Yes.
First of all, before asking my question, sir, I would like to share a little feedback from my side. Today's session was such an interesting one, but I think this was a little bit short. But I expect we will get more chances to interact with such a brilliant and motivating mind. This minutes also gave us an amazing time to interact with the person from IIT Madras. As a student member in Union Space Club and who has a deep interest in aerospace field, I enjoyed this session and saw a nice vision of our upcoming development in space frontier in a cost-effective and such a sustainable manner. So thank you for such an interesting session. Thanks to sir, and also thanks for coordinator for connecting sir and IIT Madras with us. And so finally, my question is this. what are the chances of 3D printed rockets in the future of space, especially in lunar and Martian colonization, in the special cases of lunar gate proposed by NASA?
I mean, there is no big difference, right? So whenever we go to moon, we will take a 3D printed rocket there. When we go to Mars, we will do a 3D printed rocket there. Not a problem.
Sir, is there any bigger challenges we will have to face in such a different atmosphere? And
Nothing much. It's basically, once it's 3D printed, it's as good as a current rocket. So we're essentially falling back on the same basic technology. Currently, 3D printers have a certain bed size that they come in, which is of the order of about 400 mm. Progressively, but whereas many of the rockets are actually much bigger. So you can ask the question, why is ISRO not 3D printing? The answer is, or even SpaceX for that matter, why are they not 3D printing? The answer is their rockets are much bigger. So you don't have 3D printers. Relativity Space, I mentioned one of them. Relativity Space is actually a 3D printer developing company, just to show that they can print very large engines. They are developing a very large 3D printer to build a large rocket and demonstrate. So they are the only ones which are actually making large printers, and they are exclusively using by themselves to make rockets and launch. So they became like a rocket company from being a 3D printed company instead. So otherwise, the commercially available 3D printers pose the restriction on the size. So what we do is we cluster a few rockets together to form a stage and take advantage of the modularity that it allows. But you will have a restriction on how many such engines you can cluster to go to things like Moon and Mars and all
that. Thanks.
Yeah.
Varun, I think you can proceed further. I think
yes, sir. So thank you for answering the question from our enthusiastic students, sir. It will guide us in the best way. And personally, thank you for an exciting session. We really enjoyed the session, and there was a lot to study more and more. And as we met in a Huddle Global type of an event, I'm very happy that and I'm very excited about many startups that are coming out in the area of 3D printed rocket engines and 3D printed payload making kind of industries. So we are also looking forward to it as students who have enthusiasm and curiosity in the space industry. We are also looking forward to such kind of activities. So thank you, sir. Thank you for guiding us through this topic. So once again, thanks to all students who have raised their questions, and we can move on to the next session. So I would like to invite Aditya for a vote of thanks with the permission of Shil sir. Shil sir, is there anything else to add? Yes, sir. Before inviting Aditya, I would like to announce that the quiz link will be shared through your Space Club platform just after this session, and you can attend the question quiz after the vote of thanks. And the quiz link will be also shared through the mail ID of all registered participants. The quiz will be based on the webinar of today's. So all of you try to attend that. The accurate and the fastest answer will get the prizes, exciting prizes from UL Space Club, and the prizes are sponsored by Cinderby Nurture. So please try to attend that. So that's it. I would like to welcome Aditya for the vote of thanks. Aditya, over to you.
Am I audible, sir?
You are.
First of all, good evening to all. My name is Aditya. At the first or the beginning, I would like to thank Satya sir from my behalf, because this is a topic which I have been searching for a few days, but it's a new emerging field. That's why I was not well aware of this field, because this 3D printing is used in so many nano satellites or student satellites. So I was researching on that, and this class was so enlightening for me, because even though it is a complicated topic, sir gave us the lecture which is easily understandable for a student studying in lower classes. That was so awesome and superb. I enjoyed it personally, and I convey my thanks to Satyanarayan Chakravarthy sir, the professor of IIT Madras Aerospace Engineering Department, personally and on behalf of UL Space Club. And I also thank Shajil sir, TK Kutti sir, and TK Sundaramurthy sir, and all the veterans and scientists present here, and also the student coordinators like Varunatan, Savijatan, and also all the participants who have been participated in this meeting. And this session was so the question answer session was so nice, and there was a question in that what is the importance of PSLV and GSLV? It is actually a vast question because it's at the majority of the ISRO scientists were working on that, and the major rockets were them. So I was anxious how Sa will answer that question, but Sa covered the entire portion, the major key points of that student can go on further with that points, and that answering was superb. And I also thank from my behalf for everyone present here, and also from the behalf of UL Space Club. That's all. Thank you.
Thank you.
So let's wind up today's session. Once again, thank you, Satya Chakravarthy sir, for an exciting session. Thank you so much for accepting our invitation to UL Space Club. And sir, Kutti sir, I would like to request you to mention about our webinar family to Satya sir.
Yeah, we are really excited in today's talk, and I think the number of questions unusually large and covered almost everything that you mentioned. See, this webinar has created a kind of a family outfit here. The people who are coming and giving the talk, they become naturally a part of it, and many of them, we keep them in our company and give the invite every time when the webinar is there. We'll share it with them. Not only share, we'll invite them, and many of them keep coming. So we request you to be part of the webinar family, subject, of course, your constraints of and your engagements and all those things. Then your presence will be really giving a magical impact on the students, because an IIT professor and a person who is in the frontier technologies and in this area. So we will, with your kind permission, we will keep you in the webinar family, and you will keep getting our programs. We have every second Saturday this webinar. In fact, we began it on 23rd March 2020 as every Saturday program, because in those days students had any activity, no schooling, no class. But then, at the end of that year, we found activities are getting back and students became engaged, and then we started second Saturday. It is doing very well. We will request you also to kindly sponsor some excellent people who will be interested to talk to students like this. We'll approach you, sir, for that.
Sure.
Thank you very much. It has been a very nice day for us. Very nice.
Thank you so much. Thanks
Thank you very much. We hope to have some other kind of engagements, and if our students like Varun are interested in startup also, that is why he could meet you there and strike a kind of a relationship. That is very nice. Thank you very much.
Thank you, sir. Thank you so much.
Thank you. So nice.
Thank you, sir.
Shall we leave? Yeah. Bye-bye.
Okay, bye. Thank you so much. Shajil Mash? Varun?
Yes, sir.
Varun, we have to have a online meeting